Chapter 6.2, Anti-Differentiation by Substitution. So this first sheet is just a kind of a cheat sheet of all the different integral functions and all the different integral formulas. So the first one is the power formula. So this is the one that we've been practicing. I've given an example. So if I wanted to integrate x to the fourth dx, I add 1 to the exponent. That's how I get x to the fifth. And then I divide my coefficient by my new exponent. So my coefficient here is 1. Divide that by my new exponent, which is 5. So I get 1/5 x to the fifth plus c. Sorry, I left off the plus c piece of that. I also give you the different trig formulas and their antiderivatives. I also give you the antiderivative of 1 over u, or u to the negative 1, and the exponential formulas and the integrals that will lead you to an inverse trig formula, or inverse trig function. So we're going to anti-differentiate now using substitution. So if you want to compare this to derivatives in some way, it's kind of like doing the baby mama rule, but backwards. So substitution method for integration is a change of variables can often turn an unfamiliar integral into one that can be evaluated using one of the integration formulas. So what we're going to do is we're going to take a piece of my integral, piece of this formula, and I'm going to substitute it with the letter u. So this is called u substitution. So if you ever hear or see a question that asks you to use u substitution, this is what it means. Okay. So what we're going to do is we're going to pick a portion of this equation or of this formula to substitute for u so that it is easier to find the integral of. So right now we have 3x plus 5 to the fifth power. So the way that we would normally do this is we would expand this out so that we can multiply 3x plus 2 5 times, but that's a lot of work. So instead what I'm going to do is I'm going to take 3x plus 2 and I'm going to call it u. Okay, so I'm going to take that and I'm going to call it u. Okay, so that now is something that we can integrate a lot easier. But the problem with just calling this u, right, so u is equal to 3x plus 2. The problem with calling this u is that now I can't use dx because dx was in terms of x. Now we're in terms of u. So we have to find a du that works. So in order to do this, we're going to find the derivative of u, which is 3. And since u is in terms of x, it's 3 dx. Right? Implicit differentiation. So if I'm deriving this side in terms of u, this side is in terms of x. So I have to keep that in mind, that this side is in terms of x. So the whole point in doing this is so that I can substitute something for dx that's in terms of u. Right? So I'm going to solve this for dx. So in order to do this, I'm going to divide by 3. So dx is equal to du over 3, which is the same thing as 1/3 du. Okay, so I'm taking the integral of u to the fifth power, but I'm not taking it in terms of x, I'm taking it in terms of u. So I need the 1/3 du. So dx is now going to be substituted for 1/3 du is now going to be substituted for dx. So we have 1/3 du. Okay. So this is equal to the integral 1/3 u to the 5th power du. All I did was rearrange because this is all multiplication. Alright. So now I'm going to integrate this. Right? So I'm going to add 1 to my exponent, so u to the 6th, and then divide my coefficient by my new exponent, which will give me 1/18 u to the 6th plus c. Now my final step in all of this is to put back u. So this is going to equal 1/18. I'm going to put u back, so 3x plus 2 to the 6th power plus c. Okay, I just want to make sure that at the end of this I'm putting back my u. Okay, because my original problem was in terms of x. I want to make sure that I am completing the problem in terms of x. Okay, let's do another one. So for number 2, I have the square root of 4x minus 1. Again, I have a function within a function, so I'm going to take this 4x minus 1, and that's going to be my u. So what I really have is square root of 4x, I have the integral of u, and the square root we can rewrite as 1/2 in the exponent. So I took u to be 4x minus 1. So I need to change dx so that is in terms of du. So I can take the derivative. Du is equal to 4 dx. Now I want to solve for dx. Divide by 4, divide by 4. So dx is equal to du over 4, which is just 1/4 du. So 1/4 du. So now I'm going to rewrite everything. So I have 1/4 u to the 1/2 du. And when I integrate that, add 1 to my exponent, so I have u to the 3/2, and then divide my coefficient by my new exponent. So I'll have 1/4 times 2/3, which is 2/6. Oh, sorry, 2/12, which is 1/6 plus c. And then my final step, put back u. So I have 1/6 4x minus 1 to the 3/2 plus c. So for number 3, we have options, kind of, for what u could be. Because we have an equation, a function up front with the x, a function of cosine, and then the inner function of x squared plus 5. So we want to be strategic with picking our u. Okay, what we want to do is pick one of the 3 functions, so x, cosine, or x squared plus 5, that will help us to cancel out the other. So, for example, if I take the derivative of x, I get 1. That doesn't help me get rid of the x squared plus 5 or the cosine. So that would not be a useful function to make u. Cosine would not be useful either because it's the outside function of the x squared plus 5. So the u that would make sense is x squared plus 5. So we have the integral of x cosine u, and then we're going to figure out something for dx. So we have u is equal to x squared plus 5. Du will be equal to 2x dx. So then, to find dx, we divide by 2x. So dx is equal to du over 2x, or 1 over 2x du. And if I rewrite this, I get integral of x times 1 over 2x is over 2x cosine u du. And what happens here is that this x will cancel with this x. And I'll be left with the integral of 1/2 cosine u du. So now my x is gone, right? I canceled it out using the derivative of my u function. So now I can integrate this fairly simply. So I bring out the 1/2. The antiderivative of cosine is sine of u plus c. And then my last step, put back the u. So I have 1/2 sine of x squared plus 5 plus c. Alright, for number 4, again we have to be strategic for what we pick for our u. So we have options. We could pick 3x squared. We could pick the 5 plus 2x cubed to be our u. If I find the derivative of 3x squared, that's not going to help me cancel out 5 plus 2x cubed. However, if I find the derivative of 5 plus 2x cubed, that could help me cancel out the 3x squared. So I'm going to use the 5 plus 2x cubed to be my u. So my u is going to be equal to 5 plus 2x cubed. So I have the integral 3x squared and then u to the 1/2. And we'll figure out how to change the dx. So that's in terms of u. So now we're going to take the derivative of u. So du is equal to 6x squared dx. Okay, and then dx is equal to du over 6x squared, which is equal to 1 over 6x squared du. over 6x squared du. If I rewrite this, 3x squared times 1 over 6x squared is just 3x squared over 6x squared. And then I have u to the 1/2 du. And what happens here is my x squareds cancel out. My 3 over 6 turns into 1/2. So I'm left with the integral of 1/2 u to the 1/2 du. And when I integrate that, I get, add 1 to my exponent, so u to the 3/2, multiply my coefficient by my new exponent, so 1/2 times 2/3, which is 2 over 6, which is 1/3, plus c. And then my final step, replace my u. So I have 1/3 5 plus 2x cubed to the 3/2 plus c. And that's my final answer. Now for number 5, I'm going to rewrite this so that I can really see what the functions are that I'm looking at. So I'm going to rewrite this as the integral of 1 over x times 1 over ln x dx. Now, when deciding on my u here, I have two options. I can make u x, and the derivative of that would just be 1, or I could make u ln x, and the derivative of that would be 1 over x. My personal opinion, I want to get rid of the fraction, right? So I'm going to make u ln x. And what I'm going to do here is actually find the derivative now, so that du is equal to 1 over x dx. And if I look very closely, 1 over x dx is that whole section, right? It's the 1 over x dx. So together, these two pieces are equal to du. So when I rewrite this out, I can rewrite this as 1 over u du, because my du is taking into consideration the 1 over x and the dx. So now when I integrate, I'll have the integral of 1 over u du is ln absolute value of u plus c. And now my last step is to substitute back in my u. So I have ln of ln x plus c. Okay, so that's a little shortcut also, so that you don't actually have to solve for dx if you can see that the derivative already equals the whole extra piece of the antiderivative that you wanted to cancel out. Right, so let's look at another example of that. So for number 6, I'm going to pick x squared plus 2x minus 3 as my u, because I know when I take the derivative of that, I'll get an x without an exponent. So my u is equal to x squared plus 2x minus 3. So my du is equal to 2x plus 2 dx. And if I look very closely at my antiderivative, if I can find something that can equal x plus 1 dx, that would be really helpful. So the way that I can make this equal to x plus 1 is just dividing it by 2. So du over 2 is equal to x plus 1 dx. So 1/2 du is the same as x plus 1 dx. So I'm going to rewrite this. So I have u squared, and then x plus 1 dx is just 1/2 du. So I'm just going to rearrange this, and I get 1/2 u squared du. And when I take the antiderivative of that, add 1 to my exponent, so u cubed, divide my coefficient by my new exponent, so 1/2 divided by 3 is 1/6 plus c. And now I want to substitute back in my u. So I have my final answer, 1/6 x squared plus 2x minus 3 cubed plus c. For problem number 7, I'm choosing between x and x plus 1 as my u value. So what I'm going to do is I'm actually going to have x plus 1 be my u. So u is equal to x plus 1. And then I'm going to find that derivative. So du is equal to 1 dx. So du is equal to dx. That did not help me to get rid of this x up front, because that still needs to go. However, I can rewrite x in terms of u. So if u equals x plus 1, then x is equal to u minus 1. So not only am I going to substitute u for x plus 1, I'm going to substitute u minus 1 for x. So I have u minus 1, and then I have u to the 1/2. And then dx is the same as du, so I'll rewrite that as just du. Alright, this still does not look very nice, but I can take this and distribute it into those set of parentheses. So what I'm going to do now is just distribute. So u to the 1/2 times u is u to the 3/2, and u to the 1/2 times 1 is u to the 1/2. And now I can integrate this. I know how to. So I have u to the 5/2 and 2/5 minus u to the 3/2 and 2/3 plus c. Now I'm going to substitute back in my u's. So my final answer is 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. So that was a lot of information. So I'm actually going to stop the video here, and we'll do the last page in the next video when we're substituting for definite integrals.